Hello, everyone. I can't have asked for a better presentation to go right before me because I'll touch on a lot of the same topics. And you also introduced a bunch of things that will be relevant to my talk, so thank you for that. But I'm excited to be here today to be talking about my PhD research, which is related to the hidden energy costs of set it and forget it parameters in heating, ventilation, and air conditioning, which I will refer to as HVAC. And the idea here is actually, in those buildings that you can't retrofit, or what do you do while you're waiting for the retrofit? Are there still techniques for reducing the energy consumption? So HVAC are complex systems which are simultaneously trying to control for humidity, also control temperature, and provide sufficient ventilation. So basically what it's trying to do is keep humidity at about 50%, keep your temperature at about 72 within the zones, and make sure that you have enough fresh air such that everyone stays healthy. So today I'll be focusing on this bit, which is the humidity and temperature control, for which I have found significant opportunity for savings across the contiguous US. So my work focuses on older commercial buildings, again, these that you probably aren't able to retrofit because the incentives are misaligned. And I focus on these older commercial buildings for two reasons. So first, there's a lot of energy that's used to heat and cool commercial buildings. And there are a lot of older commercial buildings, both in the US and across the world. And so globally, 12% of the final energy was used for heating and cooling of commercial buildings. In 2018, the median age of commercial buildings in the US was 37 years. And these older buildings usually have these older systems, which have limited controls. And what I mean by limited controls is that they don't have a building automation system, which means that sometimes when you want to change a setting within the system, you actually have to physically go walk into a closet and turn a knob. So this is what I mean by limited controls. And so, and what I mean by the set it and forget it parameters are basically that they rely on these rules of thumb because it is hard to change the systems. And so the set it and forget it parameters are basically when you install the system, or maybe once in a blue moon, somebody will change a setting and then basically forget about it until somebody calls and complains, or there's some kind of update to the system. A lot of these rules of thumb were developed when energy was cheap. And so basically you can imagine that they were set such that you can operate under worst case scenarios, and you don't actually have to change anything if you are at those worst case scenarios. But of course, you're usually most of the time you're not operating under worst case scenarios. And so what I'm trying to do is teach an old building new tricks. So this figure here shows the outside air conditions in a site in Texas during the last summer. And the blue line represents the amount of water that was in the outside air during that period. This red line here represents one of these set it and forget it parameters. And basically it's the amount of water that's in air at the lowest point in the air conditioning system, which is 55 degrees Fahrenheit usually is the rule of thumb. And during this period, basically on average, we needed about 38 kilojoules per kilogram of dry air in order to cool the air down to this temperature of 55. But we needed about 57 kilojoules per kilogram of water to cool down the water and condense the excess humidity. And so as you can see, the amount of energy you need for the water bit, the humidity bit, is actually much larger than the amount that you need for the dry air. And so the amount of water in your air, both mostly outside, but also indoors, can be a big driver for how much energy you may consume when you're running your HVAC system. And so at this location, during this time period, for all intents and purposes, the blue line never really crosses the red line. So it actually doesn't matter that the red line is constant. So, but that's not the case everywhere. And so here are the outside conditions at Stanford during the same period. And I'm sorry to bring up Stanford while we're at MIT, but it helps me prove my point. But the red line here is the same conditions that I showed in the previous slide. And here we can basically see that the amount of water in the outside air, first of all, is much lower than the line that we saw on the previous slide. And we can also see that the blue line actually weaves over and under the red line. And again, because this red line is constant, now we can see that there is a source of inefficiency in the system. So basically, whenever the blue line is below the red line, for example, in these cases, which are highlighted in yellow, the system is wasting energy. So all of this led to my research question of what is the potential for energy efficiency gains from updates to these set it and forget it parameters. And this is applied to HVAC in existing buildings, again, with limited controls. And so these, again, are the buildings without an automation system. So it can't just be programmed, so you can't just code up a control system. And basically, this is estimated to be about 60% of commercial building floor space in the US. So my hypothesis is that there is significant energy savings that are possible from creating location and time-specific states to the set and forget it parameters for use in these HVAC systems. So to approach this idea of updating these parameters, I needed a couple of tools in my tool belt. And first, I'm leveraging this NASA MERA2 dataset, which contains hourly data at a resolution of 0.5 degrees latitude by 0.625 degrees longitude. And it contains data for the entire world, but I'm focusing on the contiguous US. This data set includes both the specific humidity, which is basically how much water is in the outside air, as well as the air temperature at 2 meters, which is just the temperature. Basically, for these analyses, I will be using 2021 data for the entire year for both of these parameters. So the outside air conditions, as I've mentioned, are a large driver for how much energy your HVAC may consume. And I'm not going to go over all the complexities of how air conditioning works, but I do want to highlight a couple of different things which will be relevant for the rest of my talk. So first, cold water is produced in a chiller, and the chiller is the single largest piece of equipment here that consumes electricity. All the savings that I will be discussing in the next couple of slides are in terms of how much less chilled water you need to produce in order to run your air conditioning system. And then most of the magic happens in what is called an air handling unit, which sometimes you'll see referred to as an AHU. Basically, what happens is the water from the chillers goes into the cooling coils, and you have air that flows over the cooling coils, and basically you cool down the air by running it over the cold water. And the important bit here is that if your air is really humid, this is where so the temperature will go down, and then if it's really humid, your water will be condensed. Basically, cold air holds less water than warm air, and so when you cool down your air, you condense your excess humidity. And so then you have your dehumidified supply air, which is usually at about 55 degrees. And this is the parameter that I'll be changing in the future slides when I'm saying that we can update this set it and forget it parameter. We can update this 55 to something different depending on where you are and what time of the year. So after the air is dehumidified and is supplied, it goes into something called a VAV box. I won't go into the details, but the important bit here is that actually the VAV box often reheats your air before it goes into your rooms. And so you did just hear that right. Regular commercial building air conditioning will often cool down your air just to heat it back up. And the reason for that is to control the humidity. And then once it goes into the room, it'll come back out. And basically you'll have some amount of that room air that becomes exhaust air. And that some of it will actually be recycled through the system. And I'll talk about different types of recycle rates. So the recycle rate is just how much of the outside air is coming in versus how much of the indoor air is being recycled. Now if we zoom in just a bit, we can discuss sort of the second tool that I have in my tool belt, which is a data-driven physics-based model, which I can use to estimate the chilled water needed by an HVAC system. And for this model, I do need data from the building. So I need how much the airflow is, what the temperature of the rooms are, sort of parameters that you need to get from the building. But once you have those things, you can actually then estimate the chilled water load. So, and I validated this model using 5 different buildings in Texas and California. And basically what happens is I calculate the enthalpy of the air at these different points. And the enthalpy takes into account both the temperature as well as the humidity of the air. And then I attribute the differences between the enthalpies basically to the air conditioning. So it tells me the difference in the enthalpy means that the AC had to provide cooling or heating in the case of the VAV. With those parameters, I can then calculate what the chilled water load is of the HVAC system. So with this model, I can model an example building and estimate the chilled water load in different parts of the United States. And to do that, though, I need a couple of assumptions. So first, I'm assuming that all of my indoor rooms are at 72. That's sort of the rule of thumb, you might say, for what an indoor space would be comfortable at. And I'm also assuming that I can make the decision to change the set points of the AHU again. So this is like somebody going in and turning a knob. 0, 2, 3, 4, 6, and 12 times per year. And the way that I have defined these is basically described here. So the scenario names, the number refers to how many times per year you're changing the set point. And the letter refers to when those changes are happening, right? So if you change it twice a year, you could change it in January and July, or you can change it in March and September. I also assume that the AC is only going to be on when the outside temperature is actually above your 55-degree temperature set point. And also for recycle rate, I'm going to assume 50% for now, which is sort of a typical average, particularly very common in older buildings that might not have a great building envelope. So here I'm showing the results of if you're not willing to change your set point over the course of the year. So basically this is, if you're only willing to listen to me once, change it, once and then leave it for the rest of eternity. These are the savings that are possible under that case. And so there are some potential savings, but they're all mostly limited to the western part of the US, and it's about 7% of the contiguous landmass. However, in these small number of locations, you do see pretty significant savings of between 8 and 10%. So there is an opportunity to just update the set point and then promptly forget about it again, but this is pretty limited, so I wasn't happy with these results. I wanted to see if we could find more opportunity. And basically, these are the places in the US where the humidity is just never particularly high in the outside air for you to have to worry about what your indoor air humidity is. So these are the results if you are willing to violate your indoor air relative humidity constraint up to 24 times a year. What I mean by this is that you're going to increase the relative humidity inside to above 50%, about 60%. That's still well within ASHRAE comfort guidelines, and this would only be happening up to 24 times a year. But here you can basically see that there is a much larger portion of the US that now has an opportunity for, again, this is 0 changes. So basically, you want to listen to me once and then never again change this. There's some opportunity as long as you're willing to deal with some violations of indoor air relative humidity constraints. And this is about 33% of the contiguous US. And basically this again would be changing the supply air temperature of the air handling unit up to 59 degrees instead of 55. And this is very exciting because this set point change and update actually doesn't cost any money, right? You're already paying somebody to run your HVAC system. You're just telling them prioritize this, in this case, once forever, and you can find these savings. So I also wanted to understand the difference of with the potential savings as you increase the number of set point changes that you're willing to do. So this again is 50% recycle, and this is back to 0 violations. And so I've only considered up to 12, again, because the willingness to go change things more often than once a month I felt was unlikely. But here you can basically see that the savings are mostly still concentrated on the western part of the US. But as you are willing to increase your set points a larger number of times, the savings actually start shifting such that you do see savings on the East Coast. So this is just the last frame of the GIF that I just showed you. Just highlighting again the 12 changes per year, which is just once a month. And you can see that basically now the savings with 0 violations is up to 72% of the contiguous US. So there are still opportunities for savings across the entire US. So now if we zoom into a couple of specific locations, so each of these show a specific area of land within each of these states. So it's a specific plot within Colorado, specific within Nevada, etc. But basically, as you can see, the savings are very location dependent, which was illustrated by the previous slide as well. But basically, you can see that Arizona actually has the highest amount of normalized percent cooling savings possible. And this sort of makes sense because a lot of people are used to thinking of Arizona as dry heat. And so basically the humidity and the temperature are very decoupled. And the interesting bit here is basically with Arizona, if you're willing to change your set point 3 times per year with the scheme, which was 3B, basically you get the same amount of savings as if you were changing it 12 times a year, which means that you can actually change it just 3 and still get a lot of savings. And so you don't need as much work to get the max amount of savings. However, in Nevada, you do have to go up to 6 changes in order to get the same amount of savings as the monthly changes. In Colorado, however, you do have to go all the way up to 12 changes per year in order to get your maximum amount of savings. And so in New York, they're a little small, but they do exist. They're right here. But basically, it's unlikely that under this scenario of these changes, 50% recycle and 0%, zero violations, that in New York, you'd be willing to go through the effort of changing your set points for such a small amount of savings. So we can also look at the impact of allowing indoor air relative humidity constraints. So again, this is just Colorado. I'm just using this as an illustrative example. But basically, we can see that if we allow 24 violations, all of a sudden we have much higher savings. And we can get the largest amount of savings by just changing it twice a year. So that's pretty exciting because, again, twice a year is not actually that much work. And we can see up to almost a little over 10% savings in this scenario. Now, if we look, we're still looking at Colorado. Now we're going to talk about the different recycles. So basically, different buildings will have different rates of recycle. This has to do with what the purpose of the building is, what the set points have been, if things are broken or not. And so I wanted to understand if my results were still robust, looking at buildings that might have different recycle rates. And so here, the COVID mode or lab mode basically means 0% recycle. So what I'm assuming is that all of the air going through the system is outside air. So we're not taking any of the indoor air and then putting it back into the system. And basically what you can see is that when you have 0% recycle, the savings are lower for each of the different scenarios. And this makes sense because we're sort of at the mercy of what the outside air conditions are. However, interestingly and surprisingly, when you go up to 85% recycle in Colorado, you actually see that the savings are less than the 50% recycle. They're higher than the 0, but less than the 50. And that's actually because in Colorado, your outside air is actually usually between your indoor air of 72 and your low point of 55 in the air conditioning. And so basically in Colorado at this location, you have access to free cooling if you use more of the outside air. And so reducing the recycle is actually not ideal in this particular scenario. The other bit is that the energy consumption when you have higher recycle in general is usually lower, and so the savings percentage is also smaller. And then again, in Colorado, your air is dry and cold, and so that's sort of why you see this interesting and it was surprising result that the 85 is lower than the 50. So in conclusion, there is significant potential for these low-cost energy savings from updates to these set it and forget it parameters. Again, for older buildings with limited HVAC controls. These savings are both location and time dependent, as we've seen, and the results, again, are for buildings that don't have the building automation system. These savings, as you've seen, are robust in terms of looking at different types of location, different types of recycle rates, and the number of violations allowed. And basically, if places on the eastern half of the US want to try to take advantage of these sorts of savings, you do have to increase the number of times that you're willing to change the set points or be more willing to have the violations. And future work will aim to sort of quantify the magnitude of these results. So right now I'm just showing percentage savings. So I'm harmonizing another data set with building energy consumption data in order to get actual, kilowatt or mega, hopefully more than kilowatt per megawatt hour savings from these sorts of things. And I also want to drill more into the indoor air relative humidity violations to better understand how the number of violations you allow affects the results, as well as what days are being picked for when those violations occur. So with that, I'd like to thank you all for your attention and would welcome any questions.
Thank you for Rebecca's presentation. Let's take up one question.
Thank you so much for walking us through all this. So I was just interested, perhaps I missed the definition of savings. So what would be a counterfactual scenario? So let's say I want 0 violations.
Yeah.
What would be?
So this is an example. So basically what I'm doing is I'm calculating how much this, so I'm calculating the chilled water load with my model if I kept it at 55, and then calculating the chilled water load if I bring it up to 59, and just doing 55 minus 59 over 55, 10 to 100 for percentage savings. And then I'm actually normalizing over the number of days which you would actually see the savings. So here you have the savings whenever the AC is on. So actually the savings on any given day is actually much higher than those numbers I was showing. But I'm normalizing for the number of days where those savings are actually seen. So they're changing over here. So actually in New York, basically you see savings two days a year, basically, but the savings you see is like almost 60%.
Any more questions? Yeah, that's very relevant. I was curious about it. When you're talking about the violation of long units.
Yeah.
You have a sense of like how that feels in terms of thermal comfort, like is there does that feel significant or is it sort of is all?
Yeah, so I ran experiments in buildings over the last 2 summers where I did actually change the set point to 59 in order to actually measure in the building what the chilled water load savings was. For when you increase this. And this was in Houston. So basically this was one of the places where I did just increase the humidity because you have to have violations in Houston because it's always hot and humid. In terms of ASHRAE, which is sort of one of the standards that exists for what is allowed within a building. This is like the baseline rule of thumb, you're at 72 degrees, and 50% humidity. This is where the experiments went up to, which is no more than 65% relative humidity. But the temperature stayed approximately the same. We had 0 complaints over the entire summer while we were doing experiments. And humans don't have a direct way to feel humidity. We have like secondary mechanisms for it. So basically, like if you're sweating and your sweat isn't evaporating, you're going to feel that. But 65 is not high enough for that. And there's also no risk of mold growth at 65% humidity at 72 degrees.
So there is a, when you're talking about energy saving,
So the number that I was showing was cooling load. So it's the reduction in chilled water that needs to be predicted.
right? So for economic analysis, and I'm assuming that highest moving high temperature around peak hours.
Mhm.
If you can have the power save, the utility actually value that if you shave a little bit from the peak, the saving is much more than 6% energy. Because when you do energy saving, you assume 6% cost
Mhm.
on average, but it's not one-to-one. The time of use these days actually becoming much more important on the power than the energy.
Yeah, and that's a good point, except these are savings that you would see over the course of the whole day, because you're not changing it multiple, you're changing it once and sort of leaving it.
Right, but if you can look at the power load.
Yeah.
Base case versus that, if you save it, peak hours, utility actually, reward you.
Yeah.
Order of magnitude is higher than the
Yeah.
standards.
So the experiments I did in Houston were more on the, how much if we needed to shave, what it would look like. But yes, it's a very good plate for sort of future work when trying to quantify how much money you can also save. That's really important also just for reliability and resilience of the grid.
Okay, thank you. Thank you again for all this. Okay, our next speaker will be actually in the first session of future some research. She will present here that is